alternating series. In this section, we'll see another test called the alternating series test that is very useful to apply to those types of series to see if they converge or diverge. So first, let's understand what is an alternating series. An alternating series is a series whose terms are alternately positive and negative. For example, 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, etc. is an alternating series. And in fact, we can represent this series with the notation sigma n equals 1 to infinity of -1 to the n minus 1 over n. So notice how that -1 to the nth power alternates between negative and positive. And since we're starting with a positive value, we use an n minus 1 associated in the exponent of the of the -1. If it had started with a negative, we would have just had -1 to the n. So notice that this looks like our harmonic series, and in fact this is called the alternating harmonic series. And so, a question might be, well, does the alternating harmonic series converge? We know the harmonic series diverges. We've seen a couple of examples in earlier sections that explain why that is true. But what about the alternating harmonic series? Well, to determine this, we need another test. And we'll see this test on the next slide. It's called the alternating series test, amazingly enough. The alternating series test says if the alternating series sigma 1 to infinity of -1 to the n minus 1 b to the n, or b sub n, if it satisfies that b sub n plus 1 is less than or equal to b sub n for all n, and the limit as n approaches infinity of b sub n is 0, then the series is convergent. Right, so what does this mean? B sub n plus 1 is less than or equal to b sub n for all n. Each term is less than or equal to the previous term. Well, if each term is less than or equal to the previous term, then that means we have a decreasing series. All right, so notice that this b to the b sub n plus 1 and the b sub n, that's just this part, right? That's just that part right there. So forget about the fact that it's alternating. Forget about the -1 to the power. If we forget that it's alternating, if we can show that each term is less than or equal to the previous term, if it's a decreasing series, and we can show that the limit as n approaches infinity of b sub n is 0. So if the sequence of terms approaches 0, then the series is convergent. Okay, so we have, for the alternating series test, we have to show two things. Each subsequent term is less than the previous term, and the terms approach 0. If we can show that, then the series is convergent. All right, so let's see some examples. Now, before we go to the examples, notice if one of those conditions fails, if we cannot show that one of those is true, then we don't know anything. Right? We can't say anything. It doesn't necessarily mean that the series diverges, but it just means we can't use the alternating series test, in which case we will have to use some other test. Okay? All right, so let's start with the example that led into this discussion. Let's start with the alternating harmonic series. Sigma n equals 1 to infinity, -1 to the n minus 1 over n. And again, our question is, does the series converge or diverge? All right, so notice that this is equal to sigma n equals 1 to infinity of negative 1 to the n minus 1 times 1 over n. All right, so sort of separate the negative 1 to the n minus 1. And so for our alternating series test, this is the b sub n that we care about. All right, so our first question, is b sub n plus 1 less than or equal to b sub n for all n? I think it's fairly obvious here. B sub n plus 1 would be 1 over n plus 1, and b sub n would be 1 over n. And we've discussed this in the past. If we increase the denominator, everything else being held equal, if we increase the denominator, we get a lesser fraction. So this is certainly true for all n, I should say, greater than or equal to 1. All right, so that checks. Now, in later examples, this won't be so simple. So let me show another approach for this. What if we considered the function f of x equals 1 over x? We want to show that this function decreases. Is f of x equal to 1 over x decreasing for x greater than or equal to 1? So that's an alternate way to answer this question. Well, to see if a function is decreasing, in Calculus 1, we learn to apply the derivative and use the first derivative test. So f prime of x ends up being negative 1 over x to the second, and for x greater than or equal to 1, f prime of x is going to be less than 0. All right, because x squared is positive, so 1 over x squared is positive, and multiply that by a negative, and we get a negative. All right, so f prime of x is less than 0 for x is greater than or equal to 1. So f of x is decreasing for x is greater than or equal to 1. All right, so there's a couple of different approaches for that first part. All right, we've shown that each subsequent term of the series is less of the b sub n is less than the previous term. And now the second condition, we find the limit as n approaches infinity of b sub n. Well, that would be the limit with n approaching infinity of 1 over n, and that goes to 1 over infinity, which is 0. So we've shown that each subsequent term is less than the previous term. We've shown that the limit as n approaches infinity of the b sub n is 0. So therefore, by the alternating series test, sigma n equals 1 to infinity, negative 1 to the n minus 1 over n converges. So even though the harmonic series diverges, the alternating harmonic series converges by the alternating series test. Right, here's another example. Here we're given the series 1 over the square root of 2 minus 1 over the square root of 3 plus 1 over the square root of 4, etc. And we're asked, does the series converge or diverge? All right, so this is the n equals 1 term, the n equals 2 term, etc. And so it looks like I can write this as sigma n equals 1 to infinity. Notice that we have alternating signs, right? We have a positive, a negative, a positive, a negative. So we have, I'll put a negative 1 to the n minus 1 because it's starting with a positive. Now and everything else in the numerator is 1. That's not changing. But in the denominator, we have a square root, and it's not just square root of n, but the square root of n plus 1. And so I can think of that as sigma n equals 1 to infinity of negative 1 to the n minus 1 times 1 over the square root of n plus 1, and I will use that. That's my b sub n that I will consider for the alternating series test. All right, so first, is it decreasing? Well, let's see. Is b sub n plus 1 less than or equal to b sub n? Well, 1 over the square root of n plus 1 plus 1, is this less than or equal to 1 over n square root of n plus 1? Well, yes, because that's the 1 over the square root of n plus 2. And so that's a slightly larger denominator. And so that would be less than the square root of 1 over n plus 1. Now again, we could apply some calculus here. If I call f of x 1 over the square root of x plus 1, then f prime of x is negative 1/2 by x plus 1 to the negative 3/2, which is equal to negative 1 over 2 times the square root of x plus 1 cubed. Now for x greater than or equal to 1, let's consider x greater than or equal to 1, the denominator would always be positive, and so then 2 times a positive number, that's still positive. 1 divided by a positive number is still positive, and then we have that negative. So for x greater than or equal to 1, f prime of x is less than 0. So f of x is decreasing. All right, so either way you look at it, we have a decreasing series. The b sub n, I should say sequence for b sub n, that's the sequence b sub n is decreasing. Or if you look at it from the functional point of view, the function is decreasing. Our second step is the limit of b sub n as n approaches infinity, 0. The limit with n approaching infinity of 1 over the square root of n plus 1. That would be, letting n approach infinity, that's 1 over infinity, which is 0. So that checks out. We both check. So by the alternating series test, sigma n equals 1 to infinity of negative 1 to the n minus 1 over the square root of n plus 1 converges. This one's a little bit tougher, but now would be a good time to pause and try this one out on your own. All right, so here we have sigma n equals 1 to infinity of negative 1 to the n times the square root of n over 2n plus 3. This is again an alternating series, so I'm going to try to apply the alternating series test here. With my b sub n right there. That's the b sub n I'm going to consider. So I want to see, is it decreasing? So let me think. So I'll start up here. My first step, there's n in both the numerator and denominator, so this is a little bit tougher. We can't do the easy comparison here. So I'm going to use some calculus. I'm going to think of the function f of x is the square root of x over 2x plus 3, and I will calculate the derivative. So then f prime of x, using the quotient rule, I would have 2x plus 3 times 1 over 2 root x plus root x times 2 over 2x plus 3 squared. All right, to clear out the fraction, I'm going to multiply both numerator and denominator by 2 root x. So then continuing here, f prime of x is, let's see, that would give me a 2x plus 3. Root x times 2 plus times 2 times root x, that would be 4x. Over, let's see, I'd have a 2 root x and a 2x plus 3 square. The numerator simplifies further as, what, 6x plus 3 over 2 root x by 2x plus 3 squared. Oops, I made a mistake in the quotient rule. Sorry about that. That should have been a minus. That should have been a minus, meaning this should have been a minus. And then I've got a 2x minus 4x. That should have been a negative 2x plus 3. All right, so now notice that f prime of x equals 0 when x equals 3 halves. All right, so we need to see what's happening after 3, or between 0 and 3 halves, considering the domain here. Notice we've got that 2 root x in the denominator, so the domain is x must be greater than 0. Now we have that restricted domain because of the square root. And so we need to test two intervals. We've got 0 less than x less than 3 halves, and x is greater than 3 halves. And testing into the first derivative, between 0 and 3 halves, you should find that f prime of x is positive, and when x is greater than 3 halves, you should find that f prime of x is negative. And so what that tells me is f of x is decreasing on 3 halves infinity. So what that means in terms of the sequence b sub n is that the sequence is decreasing from the second term on. That's good enough, even though it's not including the first term. So what happens is it increases from the first term. We're not exactly sure if it necessarily increases from the first term to the second term. That we don't know, but I know from the second term on, I know the function, the sequence is decreasing. Okay, so f of x is decreasing on 3 halves infinity, so that tells me that root n over 2n plus 3 is decreasing for n greater than or equal to 2. All right, now the second condition, let's take the limit as n approaches infinity of b sub n. That's what root n over 2n plus 3. I think we could probably use L'Hopital's rule. I'm going to use a calculus 1 technique though and multiply by 1 over root n in both the numerator and denominator, yielding limit with n approaching infinity, and that would give me a 1 over 2 times n over root n. That would be a 2 root n plus 3 over root n. And now letting n approach infinity, the first term in the denominator would go to infinity, the second term in the denominator would go to 0, and so that would be 1 over infinity, which approaches 0. So we've shown that the b sub n is a decreasing sequence. We've shown that it approaches 0, so therefore, by the alternating series test, sigma n equals 1 to infinity of negative 1 to the n by the square root of n over 2n plus 3 converges. All right, another example. Determine whether the series converges or diverges. Sigma n equals 1 to infinity, negative 1 to the n minus 1 arctangent of n. Now, this one's a little bit different. It's not algebraic. It involves this inverse trigonometric function. And what I would notice here is, let's look at the limit first. Limit with n approaching infinity of arctangent n is not 0. It's in fact pi over 2. And so if you think about this, what's happening is, as n approaches infinity, you have a bunch of terms, and then you're adding, since it's an alternating sequence, you're adding a pi over 2, or a number close to pi over 2, and then you're subtracting a number close to pi over 2. And so it keeps on the sum. If you think about the partial sums keep on alternating between these two different numbers that aren't necessarily approaching the same value. And so since it's not 0, we can say that this diverges. All right, that concludes the presentation for this section.